Bueno, so we go with the second lecture, Philip,
Okay.
talking about supersymmetric gauge theories and Seiberg-Witten.
Yeah. So we set up this problem. We take a Lagrangian theory in asymptotically free theory, and then we can set it up so that it's a conformal theory, so it's a fixed point with a coupling that I can tune, and then I can turn on masses, and the question is, one, what happens when I change the coupling? So I go from weak coupling to strong coupling in the gauge theory. What is the shape of, what is the possible set of such theories? That's an open question, whose answer is now known in many, many examples. And I can turn on things like masses, and I start an RG flow. And we know without supersymmetry, you take a Yang-Mills theory, you turn on the gauge coupling if it's not conformally invariant, or you turn on some masses. You flow, and you generally flow to strong coupling in the infrared. And what happens is very difficult and mysterious. You develop mass gaps. You might have chiral symmetry breaking, confinement, so forth. So what happens in these theories that have a lot of supersymmetry? And I'm claiming that there is now a set of techniques using the power of supersymmetry to answer these questions. And so I want to give you a flavor for those arguments and show you some of the things that have been done. And the key is this question of these moduli spaces of vacua and keeping track of them. So maybe one thing to say, first of all, if my theory is don't turn on the RG flow, don't turn on any masses and have a conformal field theory, then it has a scale invariance. But if it has, and they will have, moduli spaces of vacua, there'll be one vacuum where all the vacuum expectation values are 0, in which case that vacuum will be the conformally invariant vacuum. But then there will be infinitely many other vacua, a whole manifold of vacua, where I turn on an expectation value. The scalars have positive dimensions, so this by hand puts in a scale for the theory. So I'm spontaneously what this is telling me is there are vacua of the theory which spontaneously break the scale invariance. And this is a typical thing that happens in these supersymmetric theories. In fact, the only examples I think we know about in more than 2 dimension, in any dimension, of conformal theories who have a moduli space of vacua with spontaneous breaking of scale symmetry are supersymmetric theories. We don't know how to control it without the supersymmetry. They may exist. It's an open question. We just don't know. So the way to think about these moduli spaces is as a kind of cone with the scale invariance, the spontaneously broken scale invariance, dictating that it's self-similar if you just scale things out in the radial direction. Because the only scales in these problems are the size of the vevs that you turn on. So let's say you have I'm just going to kind of give you this cartoon picture of how you should think about what happens to these spaces. Now, when I turn on relevant parameters like a mass, what happens is without the mass, there was an origin, the scale invariant vacuum. But once you've turned on a mass, there's nothing special about that vacuum. And what happens is it breaks up into a set of other possible, like, at least locally, they look like conical points, like scale invariant vacua. And the separation between them is governed by the only explicit mass scale we have in the problem, which is this mass parameter that we've turned on. So you can think of on distances far compared to the masses, where the vevs the expectation values of the scalars are large compared to the parameter that's breaking the scale invariance, then the shape of the manifold should asymptote to this cone. But at short distances, it instead breaks up and has some more complicated structure. And these new conical points those are the infrared fixed points, if any such fixed points do exist, of the flow. So there's this picture that if you can control these if you can understand the geometry of these moduli space of vacua as functions of their marginal couplings and relevant parameters, you get something which in some sense reflects or maps out the RG flow. And in the limit that the masses go to infinity, or in some sense in the limit as you sort of flow infinitely far into the infrared, all you're left with are a set of new fixed points, the new interacting conformal fixed points in the infrared. It's a strange picture. It's not what we're used to thinking about when we think about RG flows in a quantum field theory course, where every point in the space of theories is a theory, and then it flows along some trajectory to an infrared fixed point. Now, to every point, there is associated a property of the theory, which is a whole space of vacua, and you have to keep track of that along the flows. But this extra structure and the fact that we can control these geometries, these moduli space geometries, is what gives us the power to understand, to draw some conclusions about what the nature of these RG flows are. This, again, I emphasize, for asymptotically free or scale-invariant gauge theories, this is a strongly coupled quantum field theory problem, which generally, the only way we know how to do it is we put the theory on a lattice, right? Here we have this kind of, this interesting shortcut to understanding the result of these flows.
Theories are supersymmetric all along the flow.
They are, so that, and that's a crucial assumption that I'm going to make. A mass term for the vector multiplet scalar in a free U1 theory will break supersymmetry. There are mass terms, even for the vector multiplet scalars and for the hypermultiplets, in the non-abelian theory that will starting in the infrared. So those are the relevant deformations up here at that start the flow. By the time you get to the infrared, they're only they of course turn into irrelevant operators from the point of view of the infrared fixed point. They're not mass terms anymore. They're just some high dimension operators.
Number of supersymmetries cannot decrease, but
both, you could imagine that they decrease or could enhance. I'm going to make the assumption without proof, well, I guess I'm not doing it on this slide, but that the supersymmetry is not going to be broken. And the evidence that that's a correct assumption is just the self-consistency of the answers that I get. I don't know how to prove it. And it certainly can, and we have many, many examples now where it's accidentally enhanced along an RG flow. Yeah.
Before you told us to tune matter and to have a single beta function.
Yeah.
And then you said something about the perturbative things. Will this break running or not? Because you were saying we have one loop exact class.
No,
eventual.
Once if I tuned it so that the one loop beta function is 0, then I have then the holomorphy of the coupling told me that all the possible instanton terms also they didn't vanish; they were constant. So there's no running of the coupling non-perturbatively by this theorem. Maybe. Oops. Sorry. Here we go. If beta naught is 0, this term, the one loop things, but all of these coefficients are just constants now. It's no more complicated than that. Okay.
The idea of these drawings you make at the bottom is that you have a product.
I'm just saying, as m goes to infinity, this is a little, I don't know, fishy, but for a given mass scale of the RG flow, this is the picture of the moduli space of vacua. And all I'm saying is, if I'm interested, I can focus in on these guys. Each one individually looks like its own conformal field theory. Or I could, of course, go to very large VEVs compared to the RG scale, and then it would look like the asymptote of this. So maybe this is a misleading. Yeah, well, I put one of these for each of these points, because I can choose, do I want to focus in on this strong coupling point, or this strong coupling point, or this strong point? Okay, it's maybe not the, I wasn't trying to say something very rigorous there. I was just trying to give a picture of, just trying to get across the idea that you have an RG flow, and it's you can think of it as being mapped out or reflected by doing scaling transformations on your moduli space of vacua. But now, once you've turned on a relevant parameter, there's no longer a single point that's scale invariant. Okay, so the main thing I want to show is that these moduli spaces actually exist and persist in these theories. And here's the basic argument that works for an asymptotically free, and I can also do it for a scale invariant theory when I tune the gauge coupling to being weak. Let's take an asymptotically free theory. Then the gauge, here's the gauge coupling as a function of scale, and there's some Landau pole or something like this. I guess it's not called a Landau pole, whatever, the strong coupling scale where the one loop running gets large. I mean, you don't believe whatever's happening here once it gets to be of order 1 anyway, because you were computing it in perturbation theory. But so, and this is the problem with understanding in an asymptotically free or a Yang-Mills theory, what happens at long distances? Where does the RG flow go? The problem is you just run into strong coupling behavior. So if this is now in your non-abelian Lagrangian, so this is a function of these hypermultiplet and vector multiplet scalars are now transformed in some representation of a non-abelian gauge group. So this is a okay. Anyway, this is not the U1 example that we were doing before, where these guys were neutral fields. Then you develop some potential. It's just a matter of writing down the Lagrangian and so forth, and you find it has some flat directions. That is to say, at least classically, there are certain vacuum expectation values you can turn on without that are zeros of the potential. Because at least classically, there's zeros of the potential, so supersymmetry is not being broken there. That was this statement that if the minima are at 0 energy, then supersymmetry is not broken. And the scalars in the vector multiplets, they transform in the adjoint representation of the gauge group. And if you give a vacuum expectation value to an adjoint field, you may be familiar with from the Higgs mechanism, let's say the George I. Glashow model or something, that it Higgses the gauge group down to a bunch of U1 factors, a Maxwell theory. And of course, what these guys do, what the hypermultiplet, the squarks do, depends on what representation they're in. And here's the idea in an asymptotically free theory. If I turn on, classically, I have these flat directions. Let me turn on a very large vacuum expectation value for these fields. Very large compared to the strong coupling scale. Then what's happening is before I run down to the scale of the VEVs, my coupling is flowing, and then at this scale, it's Higgsed down to a bunch of U1s, and there may be some charge matter given. This is the dominant scale in the problem, so I'll have charged matter and stuff like this, but of masses up at this scale. And so the field content, and this is just a semi-classical computation, below this scale is now neutral with respect to the remaining gauge factors, the U1 gauge factors. So the remaining low energy couplings don't run at all. This is just like regular electromagnetism. Electromagnetism runs, but there's a lightest charged particle, the electron, and at that value where the coupling has run to 1 over 137, it stops running, and that's what its infrared value is. So this gives us confidence that we can do a weak coupling, semi-classical computation that we are confident of, because everything happens, this whole RG flow we've arranged to happen very close to weak coupling, and we found a low energy effective theory of U1s and so forth. In this computation, supersymmetry doesn't seem to be broken. We have no indication of it. It's a little hard to tell if there might be some non-perturbative contribution to this. But if supersymmetry is not broken, then not only do we have this flat direction, this moduli space of VEVs with the low energy theory at the generic point on this moduli space, at generic values of these VEVs, does not allow a potential term that would lift these flat directions. So we have found in this way, in these Lagrangian examples, that we can argue by going to weak at weak coupling for the existence of these supersymmetry protected flat directions, these moduli space geometries. And now we can ask, okay, so we have this description at weak coupling. How do they depend on, how can the terms in this effective action depend on the coupling? And again, you can change the kinetic terms, but you can't generate these potential terms. And so you're assured, or at least it looks self-consistent to say that that these flat directions are protected, no matter what the coupling is. And we will generalize this in just a second. But I'm going to skip through this a little bit. You can actually ask, what exactly do you know by supersymmetry about the dependence of things? But what you find is that the Coulomb branch, the moduli space where the scalars of the vector multiplets get VEVs, always exists in these Lagrangian theories. And at special values of the scalar VEVs, there may also exist Higgs branches. Higgs branches is my name, everybody's name, for the branches where the scalars of the hypermultiplets get VEVs. So this gives rise to this impressionistic picture of what the moduli space of one of these theories looks like. There will be some complicated nonlinear sigma model type curved manifold of vacua where the low energy theory looks like some number of U1 vector multiplets. And then at special points, say along a curve in this space, you can have Higgs branches, places where these kind of quaternionic, you can think of them as taking these hyperkähler manifolds describing the kinetic terms of the flat directions of hypermultiplets can happen. And these things don't have to be manifolds at all. They can look like manifolds intersecting one another and so forth. So if you have a region that kind of lives over a point of the Coulomb branch and it has Higgs branch directions, people call this the Higgs branch or a Higgs branch. And the Coulomb branch is the Coulomb branch, and the things that have a Higgs direction over a subspace of the Coulomb branch are called mixed branches. And in general, you can have a very complicated set of things like this. We worked this out a long time ago in the case of SUN Yang-Mills with 2n fundamental hypermultiplet, massless hypermultiplets. we mapped out all these different branches and how they touch one another and how they're modified quantum mechanically. But the takeaway thing is that the Coulomb branches persist under deformations, and the Higgs branches kind of blink in and out of existence depending on what you're doing with how you're turning on mass parameters or couplings or other things like that. Okay, so I'm going to focus on the Coulomb branches.
Sorry, what was the reason for the Higgs to
they are allowed to develop mass terms, which you can think of as potential terms. So they would just lift them from being vacua, and those.
They are not protected against generating potential.
Right. Those potential terms cannot be functions of the vevs of the hypers, but they can be functions of vevs of the vectors. So as a function of where I am on the Coulomb branch, I may or may not generate these terms, and generically I do. And so at special places, I may have Higgs branches sticking out. And then, of course, I could turn on a different relevant, a mass parameter in the UV theory for another, some other matter, and that might, and typically, generically, will just lift all the Higgs directions, but it won't lift the Coulomb directions. So the Coulomb branch in these theories with extended supersymmetry is this beautiful, it persists, and so it's this kind of a tool that we can use to track RG flows. And this is what Seiberg and Witten did in their original paper. So knowing that it exists is one thing, but how can we use it as a tool? Well, here was this effect at the generic point of the Coulomb branch. Here's this effective action. I'm not writing the fermions. Here's the U1 vectors, and here are their associated complex scalars, and it's something like this. And there was some set of properties that these guys had. And these are things that I mentioned before. And in addition, there is we said a lattice of electric and magnetic charges with a Dirac pairing. The lattice is a discrete object, so it's a kind of a fixed object. And this description, and in particular the tau ij's, transform have this kind of discrete gauge redundancy in their description called electric magnetic duality. So I'm just repeating things that I mentioned before. We can think of these properties as defining this complex geometry on this Coulomb branch moduli space. And the point is that these conditions are very constraining. This is not just any Kähler manifold. They're very rigid objects, mostly having to do with the existence of this charge lattice. Yeah. This condition here is an integrability condition for the local existence of a function, a twiddle of A's, such that tau can be written in this way. These are generally called special coordinates and dual special coordinates in the literature. Okay, so I want to very quickly take this data and turn it into reformulate it in a geometrical way, which makes things like the EM duality and all these structures kind of automatic from a geometrical perspective. And this reformulation was really due to Donaghy and Witten in '95. And the idea is we're going to realize electric magnetic duality reparametrizations of this Lagrangian, of this theory, as geometrical reparametrizations, coordinate changes of some auxiliary space, which is simply a certain complex rank R torus. So a complex torus of complex dimension R. I'll just call it A. It is, you can think of it as a complex vector space modulo translations by elements of a rank 2R lattice. So if it was rank was 1, it would be the complex plane modulo translations by a rank 2 lattice in the plane. You're probably familiar with this picture. If this just says, I'm just going to, so the basic unit cell of the lattice I can take to be a parallelogram, and this is just telling me I'm just going to periodically identify sides of the parallelogram. So that's just a one complex dimensional torus. And there's an R complex dimensional version of it. And to specify this torus, I need to embed my charge lattice in this space. Choose a basis of the charge lattice that kind of skew diagonalizes the Dirac pairing that's given on this lattice. It's always possible to do that. And then embed it in such a way that, say, that, you know, there's 2 R basis elements of this lattice. The first R you take to be, say, unit vectors in this vector space C to the R. And then to specify the remaining R, I need a complex matrix. So if E twiddles are the unit guys, the other R are some vectors, which are some linear combination, some complex linear combinations of these vectors. And that defines this matrix tau ij. And so the idea is that this matrix of couplings tau ij defines for me, I'm just using it to encode this nice geometric object, this complex torus. And what is unexpected is it wasn't just any tau ij, it was a symmetric tau ij with positive definite imaginary part, and there's this other R by R integer non-degenerate matrix that's part of this, this thing. So it's part of this Dirac pairing. And this data specify a very well-behaved class of complex tori called abelian varieties. These are complex tori that can be described by polynomial equations. Your generic complex torus cannot be written as polynomial equations in a projective space. But for a very, measure zero subset of them, they can be. And those are the ones that automatically, luckily, are the things that, that arise naturally in this, for reasons which are not really obvious why, arise naturally in this, in the low energy effective action on the Coulomb branch. So that's what I said here. So we have this picture now of our Coulomb branch. Here's my Coulomb branch. Here's a point with some coordinate A. And as I move around, there's associated to it one of these abelian varieties. And of course, because tau changes as a function of A, the shape of this abelian variety changes. So what I have is a holomorphic fibration of complex tori, of abelian varieties over my moduli space. And we call this the total space. This is a space of twice the dimension as the total space of the Coulomb branch. And this total space is the nice geometric object to describe these special Kähler geometries. I'm going through this quickly, but the key point, really pointed out by Donaghy and later by Donaghy and Witten, is that with this data, this space comes with a closed holomorphic symplectic 2 form. So this total space is actually a holomorphic symplectic manifold, like a complexification of a phase space in classical mechanics, with the variables, the A variables on the base being like the integrals of the motion, and the torus variables being the angle variables in an action angle coordinates that you may have learned about in a classical mechanics course. It's a complexified version of this. And because this description is a global description, it's telling us that this is this describes like the phase space of a classical mechanical system with a complete set of integrals of the motion. So it's an integrable system. It's the complexified version of a classical integrable system. So the weird thing, I mean, I think this is completely unexpected from looking at these special symmetric gauge theories, that the low energy effective actions on their moduli space of vacua are encoded in terms of algebraic integrable systems. And this has become a very powerful tool because mathematicians and physicists have been developing ways of constructing algebraic integrable systems for many decades. I mean, before this. And so every time you find one of these, you get a potential solution to one of these Coulomb branch geometries for these four-dimensional quantum field theories. So I wish I could give you a physics reason for why this appears. Instead, the best I know is kind of the line of reasoning that I've outlined for you here. It's really kind of mysterious. However, from a string theory point of view, there is something close to a physics understanding of this, where you have a set of theories with a little bit more supersymmetry in 6 dimensions that you get from certain string constructions, and then when you compactify those theories on Riemann surfaces, then you naturally get these structures and a description, and that compactification breaks just the right amount of supersymmetry to give you the n=2 supersymmetry in 4 dimensions. So that doesn't necessarily help because you come out from outside in terms of some string theory construction, but it gives maybe another geometrical way of understanding these things. Okay, so now we can apply, so with this long aside on just describing these class of geometries, we can now just try to classify these geometries. And here the idea is, instead of doing the hard and perhaps impossible work of actually following the RG flow in a strongly interacting quantum field theory, let's just write down all the possible geometries that satisfy these conditions, these special Kähler conditions. They are rigid enough that we can actually classify the geometries, at least in low rank cases. And then, that's not a proof, but it says for each geometry you might guess, oh, there might be a corresponding field theory. So we'll take this point of view. So first of all, let's talk about the geometries that would, the rank 1 geometries that would correspond to conformal field theories. So we're not turning on a mass parameter. Well, then they're cones. It turns out from the supersymmetry, the superconformal algebra, that the dilatation, which gives kind of the radial scaling here, gets combined with this U1R symmetry, which is also broken on the Coulomb branch and gives angular rotations. So this whole thing becomes a complex cone. And since since I'm going to restrict myself to the rank 1 case, that's it. That's all I have to say. It's this actual picture that I've drawn. It's just a flat 2-dimensional cone. It has a conformal vacuum, and all I have to say is kind of what's the opening angle of this cone if I want to tell you what the geometry is. And I think there was a question earlier, with the scale symmetry, wouldn't it say that tau is a constant? In this case, yes. Now it's strong enough to say that the low energy tau has to be just a constant on this geometry. So these are very simple geometries, but you'd say, well, I can have any opening angle, so I have continuously many. But there's this other condition, which was that there has to be this charge lattice, or equivalently, the total space had this torus fibered over it. And as I go around this space, the torus or the charge lattice has to come back to itself, right? And so, and in such a way as to preserve this Dirac pairing. And how many ways are there of doing that? And there's only a finite number of ways. The number is 7, it turns out. These have been classified by mathematicians long, long ago for a different reason, but it's the same idea. They were classifying the ways, if you have a complex surface and you have a complex torus, how can the complex torus degenerate? That's asking, as you go to the tip of that cone, what sort of things can happen to a holomorphically fibered complex torus? And those are called the Kodaira types of the singularities of elliptic surfaces. And there are 7 scale invariant ones, and here they all are. You don't have to go read Kodaira's papers to figure this out. It's just a little bit of algebra involving conjugacy classes of finite order matrices in SL2Z. And there's just these 7 conjugacy classes. I've written them all down for you. And knowing those, you can figure out things like the opening angle of the cone. You can figure out the, in terms of this, this dimension 1 scalar, the super partner to the vector boson A, you can figure out what is the single valued parameter, complex parameter on the cone. That's called the scaling coordinate of the cone. And then you can just read off its dimensions. So you see a spectrum, there's things that range from dimension 6/5 up to dimension 6. And there's a few with dimension 2 in there as well. And you can also ask, and these also fix, what are the values of this low energy tau? And they're also fixed to some specific values, except in this case here, where there's a dimension 2 scaling coordinate, where any value of tau is allowed. Okay, so I'm not asking you to absorb this table, but just to get the idea that these are very simple geometries. We can completely classify them, and we find 6 rigid geometries and one parameter continuous family of geometries. They all have the same shape, but in this case, the value of tau is allowed to vary.
Sorry, so you are saying you can write down the Lagrangian, write down the twiddle or tau in front of the kinetic, and where is it going to come into this color, whatever?
So for each of these, I'm encoding an effective Lagrangian, and if you remember in those Lagrangians, I had tau appearing in front, inside the imaginary part. I would put these particular values, but in this particular case, any tau with a positive imaginary part would be okay. Would give a consistent Coulomb branch geometry. Constant, yeah. It's constant.
This 5, 4, 3, where is this showing up in the Lagrangian? What are these numbers? I don't know if they are weights or
let's see. Well, one thing I swept under the rug is I said that the A's are local coordinates, but the A's are not single valued coordinates on the Coulomb branch. In any patch, I can simply connected patch, I can do an A. But as A's move around, they suffer a monodromy. In fact, the monodromy is related to these values of this electric magnetic duality transformation. So the idea is, if I start at a point on my Coulomb branch and I'm describing my low energy theory by some Lagrangian, when I come around, I'm coming back to the same theory, but the description in terms of the Lagrangian may now have changed by one of these discrete SL2Z transformations. And so
like a duality.
This is a duality transformation. And so in particular, the A coordinate that I started with, when I continue it around, it's not equal, it comes back not to A, but to some linear combination depending on these matrices of A and tau, an integer times A plus another integer times tau times A. So so now I can ask, what are the single valued uniformizing coordinates on this space? And the answer here, because everything is just these flat cones, the only answer can possibly be a power of any local coordinate A. And you have to, it depends on the properties of these guys, but here's the answers. I don't know if that's acceptable. It's hopefully it gives you the idea. Okay, well, so now we found an answer for scale invariant guys, and we found 7. How many did we expect? Well, we knew of 2 rank 1 scale. Rank 1, the rank of the Coulomb branch is the size of the maximal torus, the Cartan algebra of the gauge algebra. So there's only one simple gauge algebra with rank 1, that's SU2. And we know of 2 different Lagrangian field theories. There's the SU2 with 4 hypers in the fundamental, and there's the SU2 with 1 hyper in the adjoint. Those are the only ones that had the vanishing beta function. With this hyper massless, this theory actually has n equals 4 supersymmetry. So people call it the SU2 n equals 4, or sometimes they call it n equals 2 star for some reason. And this one they call it the NF equals 4 theory. So we knew we had 2 Lagrangian conformal field theories. Each of them, we had argued, has an exactly marginal parameter. And so of these things, the only theory which seemed to have a continuous family of parameters was this one. So the guess is that these geometries, this geometry would correspond to 2 different conformal field theories. And there's no idea what these other geometries are. Okay? And there's no logical problem with this. This is some observable of these 2 conformal field theories. It's possible, and in fact it happens, that their Coulomb branches just happen to be the same. That's not a logical contradiction, right? And the question is, what are these other 6? So, and in some sense, this is what Seiberg and Witten did in their original paper. They looked at these 2 SU2 theories. They did a kind of RG flow consistency argument where they started with the Yang-Mills theory, so where they've given masses, if you like, to all the hypermultiplets, and you just have pure SU2 Yang-Mills, and then they started kind of adding in lighter, more and more light hypermultiplets in one or the other of these cases, and then they build up, a picture of the Coulomb branch geometry as a function of all the masses. It's much easier to do it in retrospect from top down. You start with these scale invariant geometries, and now you say, oh, this guy should have a 4 parameter set of mass deformations because it has 4 hypermultiplets, so I can turn on 4 independent masses. And you find a family of deformations preserving special conformal invariants of that geometry. And on the other hand, this guy only has 1 hypermultiplet in the adjoint, and he only allows 1 mass. So there should be the same geometry, scale invariant geometry, should also admit a different family, a 1 parameter family of deformations preserving special Kähler invariants. Well, that's not how they did it, but that's the answer that they find. They find these 2 families. And though they didn't realize it at the time, if they had been clever about how they tuned their masses, you could have found new interacting fixed points by flowing down from the NF equals 4 theory. If you set, you let 1 mass get large and you set the other 3 masses to some special ratios or something like that and tune it, you can find a place where on the Coulomb branch, you have a new interacting fixed point. And these three fixed points here correspond precisely to these geometries. So again, maybe just going back here, this is, I'm saying you start with the NF equals 4 theory here, you turn on some pattern of masses, and you find a picture like this. And one of these red dots is one of these these interacting conformal field theories. The other ones might be infrared free theories or something like that. Okay. Let me.
So the crucial thing is that when you end up with these, you don't have marginal, except marginal.
Yeah, and these ones are rigid in that sense. They don't have exactly marginal things. These guys, they all have some number of relevant deformations, mass parameters. So this one had 4, this one has 3, 2, 1, and then the only thing you can flow down to here are infrared free theories. And this one only has 1, and you do it, and it only flows down to infrared free theories. So this is in some sense the answer long time ago. And so first of all, it's missing 3 more of the fixed points. And as I can say, just filling in 3 more isolated conformal field theories, I really want to ask, as this one shows, these 2 guys could be the same geometry, but they could admit or support different mass deformations. So what I really want to do is classify all the possible mass deformation families of these geometries. And so we did this. It took a long time. Oops. And when you do that, this is the picture that you find. So this is a result from about 10 years ago. Well, this result was found a long time ago by Minahan and Nemeshansky, and they just did this Kodaira picture that I gave you. They said, oh, there's 3 other guys, and then they worked hard and figured out some mass deformations, and the top one has a maximal mass deformation of 8 masses, and it turns out that they organize themselves to be the masses breaking a flavor symmetry, which is the exceptional group E8. So these things in brackets describe the flavor symmetry of the conformal field theory. So there's E8, E7, E6, D4, and so these all form a nice set that you can tune the masses so they all flow into one another. And the A1 theory forms another series, and these were only discovered much later. This one has an SP10, this one has an SU4, and so forth. And so it turns out you find at rank 1 a large number of conformal field theories, and you can map out the RG flows between them if you like, and only 2 of them, these 2 right here, are Lagrangian theories. The rest are strongly coupled conformal theories with no weak coupling parameters. And that's actually not the end of the story, because you can also do topological moves. You can gauge various discrete subgroups of their flavor symmetries. And if you do that, you find a ton more theories. I don't know if you really want to count them as distinct from these theories, since all you're doing is gauging a discrete symmetry, but you get different Coulomb branch geometries, or at least the deformation patterns of them in this way. Okay, so we have this now. By now, this is now a kind of a complete understanding of what's happening at rank 1. And so you can, of course, ask this question at higher rank. And, and I was going to give some indication of there's some open questions about what's the difference between these mass deformations? How do we realize distinct mass deformations of the same geometry? And from the physics point of view, it's something very simple. Take the NF equals 4 theory. if I turn on the generic four masses, then they break up into a bunch of infrared free singularities where one hypermultiplet of charge 1 at each singularity is becoming massless. But there's another mass deformation. That was the n equals 4 theory, or n equals 2 star theory. And there it only admits one deformation, and it only forms one infrared free singularity. And this corresponds to a single hypermultiplet with charge 2. And the difference between in some sense, the sum of the squares of the charges has to be the same. That's an invariant under the deformation. And it just so happens that there are two different ways of breaking up these things as written. 4 can be written either as 1 plus 1 plus 1, or rather 1 squared plus 1 squared plus 1 squared plus 1 squared, or it can be written as 2 squared. And there's this simple pattern, more or less, governing this these distinct mass deformation parameters, at least in the rank 1 case. And the generalization of this is not understood. It works very nicely for rank 1. How it works for higher ranks is kind of an open question. And I'm just going to, in light of time, I'm just going to skip over saying things, but this is an ongoing work trying to understand things at higher rank. Things get much harder as higher rank, mostly because at rank 1, we saw that there was a spontaneously broken scale plus U1R symmetry, which essentially fixed the geometry in the scale invariant case. And that's just that's not a strong enough symmetry anymore at higher ranks. Okay. How much time do I have left? $15 minutes only? Okay. Well, okay. Okay.
No, so then you have 20.
Okay, good. I will, so that was my summary of kind of more or less bringing you up to date on the state of play of this question, kind of that following along from those original papers of Seiberg-Witten and Witten, of trying to figure out the moduli, the geometry of the moduli spaces of Coulomb branches. And at low ranks, it was kind of phenomenally successful in the sense that we just classified the geometries, and then we found conformal field theories corresponding to every one. And maybe I should say a word. How do we find the conformal field theories if most of them are not even related to Lagrangian theories? Well, those came from string constructions. That's our main tool for going outside of the Lagrangian framework. And there's these beautiful brane constructions that once you kind of turn off the string coupling, you hit a non-gravitational brane theories, and you can make very convincing arguments that they're, that they correspond to these conformal field theories. Okay, so now I'm going to change topics. There's another thing, again, very old. It actually predates Seiberg and Witten, of the notion of building topological field theories by doing a twist of a supersymmetric theory. So I just want to tell you what the twist is, and then a recent way of twisting n equals 2 superconformal theories that's been very useful in the last 10 years. Yeah. Yeah.
But my impression of all that you told us, based in the presence of these Argyres structures and these complex metric tau ij that we have defined and satisfies the properties. And this complex metric is strongly based in the fact that you have an n equal 2 vector multiplet, so you can write a Lagrangian for it. In which sense you wouldn't be able to write a Lagrangian for the low energy.
So take some theory out here. This is some strongly coupled. How do we know it's strongly coupled? because we can compute anomalous dimensions of some operators we can read them off from the Coulomb branch geometry, and their anomalous dimensions are far from any free field values, okay? So this is some strongly coupled conformal fixed point, and it has a bunch of marginal deformations preserving n equals 2 supersymmetry, and it just moves us to either it flows in the infrared to some free theory or to other fixed point theories. So at least within the universe of n equals 2 supersymmetric theories, these guys at rank 1 don't seem to be connected to Lagrangian theories. There are these two Lagrangian theories, and there's some strongly coupled theories that can flow into them or they can flow out of them. Does that answer? I'm not sure if that's, maybe I'm not under, yeah.
Also start with the I0. When you start from a Lagrangian and start flowing down, you always hit a Lagrangian.
No. This is a long flow. These guys have large anomalous dimensions. You can imagine, just like the infrared theory of QCD is a theory of pions and baryons, and looks completely different from the theory of gluons. So if there's a long RG flow through strong coupling, there's just no reason that the degrees of freedom have to be organized in anything that looks like a. Yep. I think a takeaway lesson is the generic quantum field theory, and we can only say statements like this when we have a lot of control, like n equals 2 supersymmetry, is non-Lagrangian, and it's far from Lagrangian. Now you can ask, is there ways of flowing to these non-Lagrangian theories from, let's say, higher rank Lagrangian theories? And some of them you can do that and decouple factors. Another question that people have done is, can I start with Lagrangian n equals 1 theories, and could they have a flow that happens to end on one of these spots? And there are many flows that are known like this, and some of these flows are relatively short in the sense that you start with a Lagrangian theory and you still flow to, fairly strong coupling because anomalous dimensions get rather order 1, so large. But you can argue that in some sense you found a Lagrangian that was closer to this fixed point in field space. And if you throw away supersymmetry altogether, we know nothing about this. I mean, other than numerical results. Okay, so I'm going to very rapidly give you the basic idea of a twist. In whatever my supersymmetry or superconformal algebra is, pick a fermionic charge, one of the Q's or one of the S's or something like that, but pick one that's nilpotent, whose anti-commutator with itself is 0. There's many of them, but you can classify them. It's just a property of the algebra. Some of them, of course, they may close on momentum generators or something like that. We're not interested in those. We want the nilpotent supercharges. Pick one of them, and then there's a trick you can do called twisting, which is you take your theory, whatever your quantum field theory is, and you project onto only operators which are closed under the action of this supercharge. Phis which are annihilated by Q, I mean annihilated in the sense of the algebra. So the commutators with the Q is 0. And then, as I'll mention very briefly, then this sector of the theory, which I'll call T of Q, this kind of Q invariant or Q closed sector, subsector of your operator algebra, of your quantum field theory, it forms a closed subsector but what all that matters is the cohomology class of these operators. That is to say, if you modify any phis by things which are Q of another field, what we would call Q exact, then it won't change the answer for the correlation functions of these operators. So you're taking things which you have a nilpotent operator, you're looking at things which are annihilated by the nilpotent operator modulo things which are exact, which are this nilpotent operator acting on something else. That's the usual definition of a cohomology. So this twisting is the same as going to the cohomology of a nilpotent supercharge. And of course, this was made famous long ago by Witten in his, when he said, he kind of remarked that there's this topological field theory that comes from twisting n equals 2 super Yang-Mills that will, and he argued that it's going to compute the Donaldson invariance of various manifolds. So I'm going to skip over this in the light of time, but this is just a restatement of these Ward identities, and you come to the conclusion that the correlation functions in this topologically twisted theory are independent of any transformations which are Q exact, and if you find a Q closed operator, then I can act on it with any other Q closed generator of my algebra to make a new Q closed operator. So I can move my operators around and they'll stay Q closed within certain subspaces of configuration space. Okay, that's very fast. So a simple twist, the original one was in a theory with super Poincare invariance, a Yang-Mills theory, so without central charges, it turns out. There's a certain operator, I give an example of it here, which is nilpotent, and it has the property that every translation generator is Q exact. And so this tells me by these Ward identities, and I illustrated one in the last lecture, that correlation functions of an operator which is annihilated by this Q will be independent of the position of their insertions, because these all the translation generators are these topological or Q-exact operators. Those correlators are not too interesting, but there's this idea of topological descent, that if I had one of these chiral operators, then I can take its kind of super descendant by this guy, this fermion, whose Q commutator gives me the translations, and I integrate this operator over an arbitrary line, and then it gives a topological line operator, and it doesn't care about the position of the line. And I can do the same thing with surfaces and walls and so forth. And then correlation functions of the points, of the lines, the surfaces, and so forth, they can, and particularly of these surface operators, compute topological invariance of the four manifold that you put this theory on. And these are the Donaldson invariants. And then the solutions of this of Seiberg and Witten of the Coulomb branch geometry allows you to compute these things not in the difficult, strongly coupled Yang-Mills theory, as this topological sector of a Yang-Mills theory, but you do it as the topological sector of this infrared free theory on the Coulomb branch, and there it just becomes a set. You're just counting the set of solutions of some relatively simple differential equations, and those are an alternative way of computing these topological invariants, and those are called the Seiberg-Witten invariants. So the last thing I wanted to say is that about 10 years ago, Beam, Rastelli, and a whole bunch of authors looked not in supersymmetric, but in superconformal field theories. And they looked at a particular nilpotent supercharge. I give kind of one example of this equivalence class. And they have this has quite an elaborate structure of Q-exact and Q-closed generators. It has if you take a Euclidean, depending on which charge you do here, you pick out a Euclidean two-plane in space. I'll call it the x3 and x4 directions. And let me define z and z bar to be their complex combination. So I'm putting just a complex coordinate on this plane, a plane in space here. And if I look at translations, a certain combination of dilatations and boosts in the plane, or special conformal transformations, these are Q-exact, and they form an SL2 algebra. And the complex conjugate guys form another copy of SL2, and they're Q-closed but not Q-exact. So these guys move our Q-closed operators around, and these guys are the topological directions. And so what those means is that correlation functions of these operators, when placed in this plane, these are just a subset of the operators of my honest to goodness four-dimensional field theory. If I put them on a plane, these correlation functions are only depend holomorphically on the positions of these insertions. And they have this conformal invariance, the left and right moving or holomorphic and anti-holomorphic conformal groups of the plane. So these things form what's called, so their correlators form what looks like the chiral half of a two-dimensional conformal field theory. So this is the surprise, that there's a whole protected subsector of operators in any four-dimensional n equals 2 superconformal field theory, which behaves like the chiral half of a two-dimensional conformal field theory. And these chiral with certain extra regularity properties, and these are called vertex operator algebras in the math literature. And these are also very well studied, very sort of rigid objects. And just as with the Coulomb branch thing, where because the geometries were so rigid, we could classify and make correspondences with known conformal field theories, this can now be done with many vertex operator algebras. So we can talk about a known n equals 2 conformal field theory and identify exactly this infinite subsector of its operator algebra. And it's been very useful for various things, like as a starting point for the numerical bootstrap in these problems and so forth. It turns out that this topological twist, the operators which are annihilated by these charges, this double-struck Q here, turn out to be the operators that are closely associated with these Higgs branch directions, but none of them are operators associated with the Coulomb branch directions. So it's kind of funny, this vertex operator algebra seems to capture some generalization of the Higgs branch geometry, but it misses the Coulomb branch geometry, which we found. And just to advertise some relatively recent work with some collaborators, we just adapted the topological descent procedure and asked about extended operators, like line operators, that would be invariant under this algebra. And these things, these line and surface operators do indeed exist as long as you're a Minkowski signature, and plausibly have something to do with capturing Coulomb branch directions. So I'm probably out of time. I don't know. 5, okay. I wanted to, so that was, I know, too fast, but I guess I'm just saying it's an example of a hidden structure in these theories. And it's now been 30 years that we've been playing, the community, have been playing this game with these extended supersymmetry theories. And we're discovering these new structures just in the last 5-10 years. And so why is it taking us so long? Why are these extra protected structures and learning about them? Why isn't it just a straightforward, I know what my symmetry is, I have these tools, and I just kind of figure it out once and for all? Well, the problem is that there's a very basic physics problem that's been that the quantum field theory community has had to face in one way or another for a long time, for more than 50 years now, which is precisely when you have a conformal field theory, if you know, let's say you knew everything about the local operator algebra of your conformal field theory, everything about the OPEs and so forth, what property of those OPEs would tell you whether there was a moduli space along of a vacua along which the conformal invariance is spontaneously broken, which is a property of all these theories. They have this property. We know about it by, well, how do we know about it? Well, we were able to look at Lagrangian things, go to weak coupling, where we could do a semi-classical calculation, and then argue that they wouldn't be lifted, so that they're a self-consistent solution. And then after that, we applied it to strongly coupled situations, not by doing any calculation, but just by saying, let's find such geometries and see if they correspond to match to conformal field theories. And the answer turned out to be yes. So we don't understand what property we should be looking at in the conformal field theory to tell us about the existence of flat directions. This is a very basic open problem. I guess I'll just put it out there as a challenge. How would you go about answering a question like this? You might say, well, if we have spontaneously broken scale invariance, then any size of the VEV is related by scale invariance. So I can scale this thing into 0, which is the conformal thing. So isn't it connected? Don't I just kind of scale it into 0, and then and it will tell me what the property is at the conformal vacuum in terms of the conformal spectrum. And the problem is that no, you can't. Because of the spontaneously broken scale invariance, there's a discontinuity between non-zero VEV and zero VEV. There's no way of continuously making a non-zero VEV 0, because as you scale it in, it's self-similar by the broken scale invariance. So changing this VEV has no physical difference. The spectrum out at non-zero VEV is some discrete spectrum of massive particles with masses proportional to the size of the VEV, because the VEV is the only scale in the problem. It just becomes self-similar, and something qualitatively different happens right at 0, where all of these things combine into a continuous spectrum of a conformal field theory. It's a very difficult problem. Another way of saying it is, if you don't have a Lagrangian or a weakly coupled description, we don't know how to use conformal data to construct the notion of an effective potential. How do you do that, given the operator algebra of a conformal field theory? So I think this is a key problem that's been the key stumbling block in this whole thing. It's why this whole subject has this feeling of constant little discoveries, because what people end up doing is you discover a geometry or one of these vertex operator algebras or something, and then you say, what could this correspond to in the conformal field theory? And then you have to make up a dictionary between the two and ask about consistency questions. And you don't have an algorithm for saying, oh, only these properties are consistent with conformal invariance. I'm probably out of time now. I had a bunch of other things, but open questions. There's many conjectures along these lines of geometrical properties of, say, Coulomb branch geometries, and these are all open questions. A very simple one is, every time you have a theory every example we know of a theory with a conformal manifold, that is to say an exactly marginal perturbation, there's always some value of that coupling, which can be interpreted as a weak coupling Lagrangian theory, or at least as a gauge coupling where a gauge coupling is becoming weak. Why? Nobody knows. So it's conjectured that that's true, but we don't know if it's true or not. And there's similar things like that. There's the classification. I'm going to skip over these things. Oh, and maybe this is a good one to end with. I talked about the two derivative terms, the kinetic terms in the low energy effective action. And those were nicely protected by supersymmetry, so they were the leading terms and the natural ones to look at. But you could ask about higher derivative terms, 3, 4 derivative terms. I mean, 3 derivative means 2 derivatives and 2 fermions, and so forth. And some of those are also protected by supersymmetry. So those, you would imagine, can also be understood. They give some sort of, you can maybe interpret them as extra geometrical structures on the Coulomb branch that can be computed exactly. So in some sense, this is a sequence of other observables which we have the potential to compute exactly in these strongly coupled gauge theories. And there's been very little work on that. Only a few cases with n equals 4 supersymmetry, the 4 derivative terms have been computed, and all the other cases, there's basically nothing that's known. So this is, I think, a ripe open problem for someone who's strong. And I'll just end with this slide. There's many things in this subject that I just haven't brought up or just mentioned briefly. And at the bottom there are some of my favorite reviews of topics having to do with n equals 2 supersymmetry.